You actually come here out of fear that you might lose your job to an AI robot someday. So I would ensure that this is actually going to be a great conference. We not only have the best lineup of speakers from both semiconductors and AI field. So we have the VP and GM of the world's largest semiconductor company to speak. We also have fellows, directors, distinguished engineers from chip design companies. We have our distinguished technologist and turned VC in the field. So what else can you expect more for a conference? Now, without further ado, let's welcome Dr. Li to give our keynote speech. Thank you.
Okay, you can hear me, right? Sorry for the technical difficulty here. So thank you for coming on a Saturday afternoon. Am I standing too close to you? Okay. All right. So before I came here, I was trying to prepare slides for this conference. I was trying to figure out what should I tell you. Then I brought in a few slides, and when I got here, I ran into people. People said, "What for artificial intelligence?" Then it just occurred to me I've got the right slides here today. I hope all of you, and I'm afraid all of you, have the same addiction as I have, which is you have to carry something all the time. You have to carry something. You have to carry something 24 hours a day, 7 days a week. And if you have not listened to the instruction yet, it may actually rain during my presentation today. And by the way, I'm not talking about drugs here. Okay? Now, studies show that. So studies show that an average user like us, we're all connected all the time, online, every day, every night. By 2020, we will be generating 1.5 gigabytes of traffic every day. And there are a lot of us humans in this world here. Now, much more than that, there are all kinds of things being developed. Internet of Things. For example, you have a self-driving car. We're lucky to live in the Bay Area. We often see self-driving cars around us. A self-driving car will generate somewhere around 4 terabytes of traffic every day by 2020. When you look further, smart factory with connected robotics inside will generate more than 1 petabytes of data, petabytes of traffic a day. When I saw the data first time, I actually had to look up the word petabyte to see how many zeros we have in the petabyte. So what do we do with all this data? Years ago, we would just keep the data in a database somewhere. And we would do things like select attendee's name and their salary. So somebody, maybe a president here, will do the search like this, and we'll find out how much each of you is making here. I used to manage a software team where we actually worked with a major database vendor to optimize databases so we can do these transactions quickly. At that time, we set a world record using 64 CPUs. It was considered a supercomputer at that time. Fast forward to today, I have a team working on machine learning in the cloud. And the goal we have here is we try to take 1,000 nodes, 1,000 CPU nodes, which is roughly 100,000 vCPUs. So when you go to the cloud, you are being charged for number of vCPUs, virtual CPUs you have. So you're getting roughly 100,000 vCPUs and we try to see how far we can do, how fast we can do machine learning training on the cloud. So in the past 10, 20 years, things have changed. We have seen much more data, and the compute capacity changed also. It's easily we can get so many CPUs, so many compute units. And the kind of workloads have changed as well. It used to be more of a transactional-based workloads. Now we are looking at artificial intelligence. So AI has come back because we have more data, we have more compute, and there's a lot of computation, a lot of innovation inside the AI community. And I was actually trying to register for the NIPS conference, one of the major machine learning conferences. Even 3-4 months in advance, it was just sold out. There's so many interest, so much interest. A lot of people want to get in there. There's a lot of paper being published. What can AI do? So AI, you can imagine, AI can transform basically every aspect of our lives here. From the consumer side to health to transportation, basically anything you can think of, AI one day will change it. The opportunities are boundless, and the sky is the limit. Actually, more than that, AI is already here. It's already happening. I went to visit Stanford Medical School a few months ago, and saw AI can actually read X-ray images better than an average radiologist. So if you're thinking about changing your career from an engineer to a radiologist, you better think twice here. I have a team that is working on mobile devices, things like smartphones and tablets. As part of that particular project, we have to do testing. So initially, we actually hire people to do testing here. And the job initially sounded very fun, right? So when I told my kids, we're hiring people to do testing to play games, and my son said, "Can you hire me? You get paid to play games." But it turned out to be, it's not a very exciting job. So I have one case where we hire somebody, he quit on the same day. So it is expensive for us, and also it is very slow. So what we did was we actually developed a robot to do testing automatically. And we use AI to do testing, and the robot can actually find more bugs than human testers. And the robot can work 24 hours a day, 7 days a week. And the robot never complains. Never complains about the working conditions, never asks for pay raise. So it works out very nicely and for the project we have here. So how does AI work? I know a lot of you probably interested in AI may already have, gone to training and learn about AI. I just want to give you one example so we all come on the same, we're all on the same page. The example I give here is deep learning. You may already have heard of deep learning. Deep learning is a very interesting sub-area of AI. And the goal of deep learning is something like let's say we want to develop a model. And the model will do is, for something like you take a picture, the model can tell you whether the picture has a person in it or the picture has a dog in it. And we have two different phases when you work on deep learning. The first phase is you want to train the model, and the second phase is once you have the model who can answer all these questions, and then you will deploy the model in whatever application you have, maybe in the self-driving vehicle, for example. On the training side, you will take some effort to train a model, because initially, so deep learning is basically a, getting noise here. Deep learning is basically a mathematical model that looks like a neural network. Eventually, it's just a mathematical model here. You need to train the model in such a way that they will learn and eventually figure out what to do here. And the training takes a lot of time. Usually, you feed in a lot of images and you feed in a lot of labeled data, and initially the model gets wrong, and eventually it will self-correct and get you the right answer. Because the large amount of computation involved, it's usually run on the data center, where you have powerful computers. Once you have come up with a model, you deploy it. You can deploy it for inference either on the data center somewhere, or you can deploy it on the edge device somewhere. Could be your whatever device you happen to carry. So there are a lot of opportunities for all of us, particularly all of us who are in the semiconductor industry, on both hardware side as well as the software side. And many people trying to get into. And if I look at the number of attendees for this conference, I hope you're all here because you're interested in AI. There's so, the big companies trying to get into, like our company, and the smaller companies are trying to get into. And every day I run into so many people who want to do a startup on AI. So there's so much interest here and so many opportunities. So let me just share with you a little bit of what we do inside Intel. So first I'll talk to you about on the hardware side, then I explain on the software side what we do. On the hardware side, our approach is we take a portfolio approach of multiple products and to cover the entire spectrum from the data center to the edge. And you all know Intel is a CPU company. But we do more than CPU here. And if you look at the products we are building here, some of them can be used on the entire spectrum. Some of them can be used on the data center side all the way to the client and the edge side. For example, Xeon processors and FPGA, these can all be used in all different scenarios here. And some of these we actually designed for particular usage. For example, some product we designed it for data center deep learning training. And some products we designing them for edge usages like computer vision or natural language processing. So I'll talk to you about, get into details on some of these. So let's look at Xeon first. And you probably have known Xeon for a long time. If you have a data center, most likely you have Xeon. Now Xeon is powering the vast majority of cloud and data centers around the world. So it's widely used there. I met with a few cloud service providers recently, a few weeks ago. And I asked them what kind of applications, what kind of workloads you run in your cloud or in your data center. And some of them said, I don't even know, and I don't even care, because they have to support all kinds of workloads coming into the cloud or coming into the data center. I have worked with the Xeon CPU team for more than 10 years, and one of the things they really want to make sure is we will run all applications, all workloads well on Xeon. And on top of this, they want to make sure from generation to generation, we provide meaningful performance gain over the previous generation. So most recently, we had a new generation of Xeon announced a few months ago, and particularly for artificial intelligence, deep learning training, because of the combined hardware improvement and software improvement we have done, we have been able to see up to 100x performance gain over the previous system, probably 2-3-year-old system there. So that's a huge performance change. And I'm very proud actually my team contributed to this particular large performance gain. So what does that mean for users who want to, for example, use Xeon for machine learning training? So that means if you, a year ago, tried to run machine learning training on a processor, it may take you days, many days to do, and now you can finish it actually in hours with the right optimized software and the latest processor. Now, what if all you do is deep learning? Then you may want to consider an accelerator. So last week, Intel actually announced the new Nirvana neural network processor. And this is designed by a group of people Intel acquired last year. The Nirvana company Intel acquired last year. And these are a group of very cool people actually. So lucky to be able to work with them for the last year. And I never met so many neuroscience PhDs in my life before that. So the Nirvana chip was designed from scratch for deep learning only. So it is very much specialized for deep learning. As a result, you can get rid of a whole bunch of things we used to have to do for non-deep learning specific chips. So it could be very much targeted, and as a result, you can pack a lot of compute on the chip here. So the compute density is very high. And it also has separate pipelines, one for computation and one for data management. For those of you who are in engineering, you know it's more than computation. If you end up waiting for data to come in, you're idle here, right? It's because we have separate pipelines. The new data is always there when you need to do computation. And as a result, we're expecting near the theoretical peak when you get to efficiency. Machine learning training also involves moving a lot of data, both from memory and also from your other neighbors. So this chip also has two additional features. One is it has high bandwidth memory. It has both high capacity, also high speed. And it has also very high interconnect among the compute nodes. How about on the edge side? We also have specific accelerator for edge devices. A few weeks ago, Google announced a new camera, smart camera called Google Clips, which is I'm showing right here. Wow, this thing I'm showing right here. What this camera can do is you can clip on pretty much. So it's mobile and has AI in it. It will do image recognition. So if grandma comes, it will automatically recognize this is grandma and take a picture of her. If some stranger comes, it may not even take a picture. So it has some smart inside to do face recognition. Because it's an edge device, you need power consumption is an issue. You cannot plug a power supply to this. So what we happen to have is Intel has a accelerator called Mobilius, which is a very ultra low power, and that happened to be inside the Google device here. Now, having hardware itself is not sufficient. We need software around it. And luckily, within Intel, we actually have a lot of software people. And what do we do here? So we work with hardware people very closely. For example, I already mentioned to you, we do co-design with the hardware architects, and we want to make sure they design in the right thing for the customers. And once we have the silicon, we do 4 other things around it. So one is we work with the community. We work with the developer community, or we work with the research community. A few weeks ago, I attended a Stanford research retreat to see what kind of research they are doing to make it easier, make AI practical. And we also work with different partners to develop solutions. For example, we work with certain banks to design fraud detection applications. And we have a lot of people doing optimizations. And we are optimizing the various operating systems. We're optimizing a lot of databases I mentioned earlier. We're optimizing all kinds of applications. Quite often, the application engineers in the group, we actually have access to the source code, so they can sit side by side with the ISV and the engineers from the ISVs. And on top of all of this, Intel actually delivers software products. And we deliver products like the Intel compiler, we deliver products like the performance analysis tools. If you want to tune performance, you want to understand where your performance bottlenecks are. So let's talk about the community side. So we have something specifically for AI. We have something called Intel Nirvana Academy, where all of you can actually go and attend training seminars to learn what AI is, and to also get the tools and the software Intel has provided on the website. Most recently, at the O'Reilly conference, we also announced that Intel is making a Intel Nirvana Dev Cloud available. So that allow you to get into a cloud to run with all the software we're providing to run machine learning, training and inferences in the cloud here. So how about the software side? So we cover the entire software stack. At the lowest level, you have all these libraries. And usually these libraries are developed in such a way that it makes use of the hardware features. They are the closest to the hardware that we have. And then for machine learning, particularly deep learning, we have all these frameworks from TensorFlow, Caffe, and so on. So the data scientists usually, they don't do C++ programming. They actually use these machine learning, deep learning frameworks. They call these APIs. And these APIs are optimized using the libraries. And then on top of that, we actually provide various development platforms. For example, we have software to manage the AI cloud, and we have software to manage the entire development process, starting from data all the way to deployment. And along the way, it will help you figure out what kind of model you want to have, and you can actually assist you on the training side and the deployment side. So let me look at something specifically. So all these frameworks, how do we optimize for these? So when you get into underneath these frameworks, what you will find out is they are actually a lot of math functions. The deep learning itself eventually is a lot of math functions. It's very similar to actually high performance computing. So I spent quite a bit of time in my career on high performance computing, supercomputing, where we want to run these mathematical functions quickly on supercomputers. So the issues in the deep learning side are actually very similar. You want to parallelize your computation, you want to make sure you manage your communication efficiently, you want to take care of data localities. All of these technical issues are actually very similar inside deep learning. Intel has been in the high performance computing area for a long time. In that community, they maintain a list of top 500 supercomputers. And Intel's processors are in more than 90% of these supercomputers. And every one of those has Intel software in it. In this case, the math kernel library. So what we wanted to do was to address the deep learning challenge. We want to leverage what we have done on the HPC side, and we created a new library on top of this called MKLDNN, which stands for the math kernel libraries for deep neural networks. And that is a open source project. Anybody can also contribute to it. And that library has all the necessary computational primitives. And we do something similar for the communication side as well. So what does that mean from performance perspective once we optimize for those? Now, many of you probably have a lot of Xeons, as I mentioned earlier. Xeon is powering, majority of the cloud and data centers. So people have a lot of Xeons around. So what we want to find out is, if you have all these Xeons, how much performance can you get? So a research group in Europe took our software and applied their creativity. And they actually managed to take a topology from deep learning called ResNet. ResNet is one of the very popular deep learning topologies. And they ran it, and they can scale all the way to 500 nodes. And the training time was only 44 minutes. So the training time here is one of the best in the world for running ResNet 50. And also you can see in Europe, they have really style. Even in the computing center, the building is much nicer than the building I'm in, actually. So we have all the hardware and software. We all have all these technologies. What does that mean? What can we apply to something useful here? All of us have seen natural disasters. Actually, unfortunately, a lot of natural disasters this year, including the fire in north of us. My neighbor moved to Napa about 10 years ago. So he was lucky to move out of Napa just a few months earlier. But one of his friends, who's 86-year-old doctor, did not survive the fire. A few months ago, a company came to Intel. They said they want to design a drone to do something interesting. In this case, they want to send drones to do some high-risk jobs. For example, they want to send a drone to inspect highway bridge to see if there are damages. And they want to send a drone to inspect where the power lines have come down. And they want to send the drones to inspect the exterior of airplanes, and instead of human climbing a ladder to do this. My team worked on the model for them. And we managed to train the model using the CAFE framework we have optimized on Skylake. So on a single node Skylake, we were able to finish training just in hours, just in 5-6 hours. So with the technology we have, we can already make a huge difference. And just imagine if we use these drones for these natural disasters, how much life we can save here. So AI has huge potential. And there are a lot of opportunities for all of us here on both the hardware side and the software side. And working together, we can unleash the next wave of AI. Thank you.
Thank you, Dr. Li. Don't tell my boss about this, but I also applied for that job you were talking about. The one that played video game 24/7? Yeah, so I would...
Sorry, it's too late.
Yeah. Very sorry you actually hired a robot to do that job. Okay, so At this time, given the time constraint, we're going to open the floor for just one question. If we have more time later, then we can do that. So there are two microphones, one on this aisle and one on that. So if you have a question, please step to the microphone. And this is your opportunity to get as much information out of the Intel, Dr. Li, without signing an NDA. So please. Go ahead. Yeah, that man in blue. You can try to speak about where you are.
I'll speak up.
Okay.
What are the difference between the GPU, FPGA, and a special hard architecture for using hardware to speed up their machine learning? What are the differences? What are the trends in the future for them?
Okay.
Which
So
one of them?
the question is, what are the differences among all the things I talked about earlier? I'll just extend your question a little bit. So each actually plays a different role. So for example, I didn't get a chance to talk about FPGA at all, right? I just sort of mentioned FPGA. So FPGA has something very unique where you can actually customize it. So Microsoft actually announced a project recently called Brainwave. I don't know whether we're Microsoft people here or not. Where they actually use FPGA, in this case happen to be our FPGA, in the data center for deep learning inference. Now the reasons they went for FPGA, I was talking to them actually earlier. The two reasons that stand out for me. One is you can customize your FPGA for the particular inference algorithm you happen to have. So in deep learning, for example, for inference, sometimes people use different precisions, right? That you don't necessarily use FP32. You could be using FP16. You could be using 4 bits even. Sometimes people are writing papers for 2 bits, and so there are different numerical format you can use, and these are not necessarily available in the existing CPU or existing ASIC. So in that case, they just pick FPGA to do this. And the other good reason for FPGA is machine learning is a fast-moving area, and particularly if you're in research. I hope some of you probably in research here. Every day you come up with new ideas. You want to do something, right? And you can't wait for a processor or GPU to react that quickly. So they actually do it. You can reprogram FPGA, and quite often they can do it in 2-3 weeks, for example. So that's just why you want to choose FPGA, but there are different reasons for other offerings as well.
So at this time, I'd like to invite our President James to present a token of appreciation to Dr. Li.